Now let's dive into the radiative model of the Earth's climate system. This video is in 4 sections, each of which is fairly technical and explains the details of radiative transfer. This is almost all concentrated on the effects of water vapor and carbon dioxide. CO2 is a critical gas for life on our planet. It's amazing. Even though there are only 4 in 10,000 molecules, carbon is everywhere around us. All of us are almost certainly sitting on or within a few meters of some carbon-based material right now. For example, wood, limestone, concrete, plants, paper, food, animals, humans, even bunnies and carrots, all of it comes from the tiny amount of CO2 in our atmosphere. Now I want to describe the greenhouse effect. I'll try to make it simple, but in reality, it's very complex. The radiative model uses the energy balance diagram we're used to seeing. That red strip on the right represents back radiation, which sends energy back down to the surface and keeps the surface warmer than it would be otherwise. So let's start at the beginning. A high-energy short-wave photon comes in from the sun after its 8-minute journey through space. When it hits an object, like a rock, the high-energy photon is annihilated and heats the rock, which then radiates long-wave photons according to its temperature. One short-wave photon generates about 20 long-wave photons, which have much less energy. If the outgoing photon happens to be in the right wavelength of 10 to 14 microns, then it leaves to space unimpeded. About 12% of photons go straight to space that way without adding to the temperature. Second, the photon can't hit an air molecule like nitrogen or oxygen and transfer its energy to that air molecule. That's impossible. These atmospheric molecules are transparent to both shortwave and infrared radiation. The photon can only interact with greenhouse molecules. When the photon encounters a greenhouse gas molecule, and I'll use carbon dioxide as an example, this dipolar molecule absorbs the photon and begins to vibrate at a higher energy state. This is a quantum phenomenon called vibrational transition. Now, 2 possible things can happen. First, that vibrating CO2 molecule could hit an air molecule and transfer its energy mechanically via collision, so the air molecule speeds up, increasing the air temperature. This is like a billiard ball hitting another billiard ball. The first ball comes to rest and transfers all its energy to the other ball. This is called thermalization because the vibrational energy turns into velocity, which is temperature. In the second possibility, the CO2 molecule spontaneously de-energizes, and that re-radiates a new long-wave photon out in some random direction, and then it goes back to its previous energy state. The energy of the photon corresponds to the energy lost by the molecule. This is the radiative model. Greenhouse gas molecules are constantly absorbing and re-radiating long-wave photons, so the energy makes a random walk up through the atmosphere to the top, where it's finally emitted and goes to space. But this is just radiation. It's just photons. They don't change the air temperature at all. As those higher energy greenhouse gas molecules encounter air molecules, they transfer energy mechanically, thermalizing the energy, and that increases the air temperature. So let's understand that process. Again, a long-wave photon coming from the surface at the bottom energizes a CO2 molecule near the surface. On average, it takes that energized molecule about half a second, maybe even a little longer, before that molecule de-energizes and re-radiates a photon. Okay, but long before that, the CO2 molecule is struck by an air molecule and transfers its energy mechanically, heating the air. So the collision almost always happens first, increasing the speed of the air molecules. The warmer air rises by convection. Eventually, all that air transfers its energy back to a greenhouse molecule at the top, and the energy is radiated out to space. But CO2 is a well-mixed gas. There are CO2 and water molecules up and down the air column, and they're emitting long-wave photons all the time. Some of these photons get radiated back down to the surface and start over. Water vapor does most of this, and CO2 does a small amount, within their respective wavelength ranges, which we'll soon learn about. Because energy is always conserved, this doesn't add more energy. It just helps keep some percentage of the energy lower down near the surface before it escapes. This is the actual greenhouse effect. It slows cooling, keeping surface temperatures higher than they would be otherwise. The effect is most noticeable at night. At the top of the atmosphere, there are far fewer air molecules and much less water vapor. At some point, an air molecule bumps into a greenhouse gas molecule that finally emits a photon that goes off to space without hitting anything else. The average height where most heat is dethermalized and sent to space is called the emission height. But the actual height can vary by several kilometers. This is how about 99% of the energy arriving on Earth eventually leaves to space through dethermalization via a greenhouse gas molecule at the top of the atmosphere. And it turns out that there's much more CO2 at the top, so CO2 dethermalizes most of the energy. Adding more CO2 can and does raise the emission height more, but in reality, because the molecules are so spread out up there, adding CO2 hardly changes the surface temperature at all. But the Earth's surface is predominantly water, so we have to understand what happens in the oceans. Wherever there's a lake or an ocean, some incoming photons hit a water molecule on the surface and evaporate it, sending it up into the air. From there, the moist air expands and rises as convection moves the expanding air upward. As it gets higher and colder, water vapor condenses into droplets that form clouds, and that condensation releases energy, which is then dethermalized by a CO2 or water molecule and sent to space. There's no CO2 required at the beginning, it's just sunlight evaporating water from the surface. Now here's the picture in the oceans. About 10% of sunlight hitting the oceans reflects back to space, like a mirror. 20% is vaporized on the surface and rises into the atmosphere. About 50% of the photons penetrate the upper layer of water to about 10 meters, and about 20% more make their way into deeper ocean layers. Oceans cover 70% of the surface, and the oceans absorb 70% of that incoming energy. We'll come back to ocean heating in a minute, but first, we need to deepen our understanding of the role of both water vapor and CO2 in the atmosphere. To explore the greenhouse effect further, let's look at water vapor versus CO2 and their actions as greenhouse gases. In a clear sky like this, almost all the water vapor in the air exists as single molecules. These single molecules can become very cold, but they don't freeze. It's practically impossible for single molecules to freeze in the lower atmosphere. So even though it's very cold, they can still do plenty of work absorbing, thermalizing, and re-radiating infrared energy. This can even happen up in the stratosphere because the stratosphere gets less cold as you go up. These curves show the spontaneous emissions of photons from the surface at various wavelengths, from 1 micron to 50 microns, from short to long wavelength, according to different latitudes. The top curve is the equator, which emits the most because it gets the most incoming sunlight, and the bottom green curve is for the North Pole. This is the infrared spectrum emitted from the surface at each of these latitudes, averaged over land and water. It's like a histogram of the number of photons going upward at each wavelength and according to each latitude. Only a small percentage of these photons are in the right wavelength for CO2 to absorb them. CO2 can't have any effect on about 90% of all the energy in the atmosphere. It's very limited in what it can do. Water vapor, on the other hand, absorbs far more energy. Water vapor can absorb and re-radiate many times more long-wave photons than CO2 can because its various vibrational states are better suited to absorbing energy in all these different wavelengths. Now we need to look at concentrations of the greenhouse gases by altitude. The red line is CO2. It's a well-mixed gas at the same concentration from surface to the top of the atmosphere, all the way practically to space. At the moment, it's around 420 parts per million, which is 4 out of 10,000 molecules. At the surface, water vapor is 10 to 50 times more abundant than CO2, and it covers much more spectrum. But there's 1,000 times less water vapor in the upper atmosphere, whereas CO2 never changes. After just 8 kilometers, CO2 is more abundant than water vapor. Methane has no real effect, but ozone, the golden line we see here, is abundant in the stratosphere and does about 4% of the work of the greenhouse effect. The same thing happens latitudinally. Water vapor is very highly concentrated in the tropics and very sparse at the poles. So there's a lot of water vapor lower down near the surface and in the tropics, and less as you go up and poleward. The white area here represents where CO2 is more prevalent than water vapor. To summarize this, we say that on average, water vapor does most of the work to keep the surface warm, but overall, CO2 is responsible for just about 20% of the total greenhouse effect, most of that higher in the atmosphere. And remember, CO2 only re-radiates in a very narrow part of the spectrum. CO2 is very limited in what it can do, but molecule for molecule, it does a lot of work in the atmosphere. Even though the poles are very dry, there's still water vapor at the poles in the lower altitudes and even higher up. Water vapor is almost never frozen at the surface because it takes extremely low temperatures to turn water vapor into ice. So even at the poles, water vapor is responsible for more of the greenhouse effect than CO2 is. Now I want to apply the theory we've just learned to real-world data from the Ceres satellites. The poles are generally under clear skies. In July, the Ceres satellite instruments measure about 200 watts per meter of downwelling long-wave radiation going to the Arctic surface. During those months, the North Pole receives sunlight all the time, so the atmosphere there has a fairly active greenhouse effect. And by the way, when we talk about watts per square meter, we have to keep in mind this is long wave, not short wave radiation. You can't compare long wave watts per square meter to incoming sunlight because long wave photons can't penetrate the oceans. They are for going up, not down. And this is a common mistake because these numbers are not comparable. During the darkness of January, there's a temperature inversion almost all the time, and the poles are busy getting rid of heat stored over the summer. Still, there are about 100 watts per square meter of long-wave radiation being re-radiated downward. At that time, water vapor still outperforms CO2 in sending radiation down to the surface by about 2 to 1. That is the greenhouse effect. So even the poles in winter would be colder without the tiny amount of CO2, water, and ozone higher up. This is the real greenhouse effect. It helps keep nighttime temperatures less cold than they would be otherwise. In Antarctica, during January, warm air is coming in from the temperate zones on its way from the tropics, and that mechanical energy sends more radiation down to the surface via the greenhouse effect. Recall that in January, Antarctica is in summer. Antarctica is the driest place on Earth, but there's still water molecules in the air and they dominate the greenhouse effect. Now, during July, when it's winter, it's even colder here than in the Arctic. Why? Because Antarctica is that much colder and higher. Average elevation in Antarctica is about 8,000 feet, so there's less atmosphere in Antarctica. At sea level, it's a bit less cold than on the plateau. In the Sahara Desert, skies are usually clear, and there's very little water vapor. During the day, sunshine puts a huge amount of energy into the system, and some of it is re-radiated back down, which makes the surface warmer than it would be otherwise. At night in the Sahara, it's cold. If you've ever spent a night in the desert, you know it's cold, but the air is much warmer than at the poles, which is why the numbers are higher. It's less cold at night than it would be without the greenhouse effect. I'm not going to translate watts per square meter into degrees because that's where all the fudging is. There are too many factors to do that with any accuracy. But here we see quite a lot of downwelling radiation at night, even under clear skies. This is the greenhouse effect. In the rainforest, there's a smaller difference between day and night because water vapor is doing most of the work to keep sending energy back down, delaying its escape to space. During the day, evaporation pumps most of the energy into clouds and up to the top of the atmosphere to escape. At night, the greenhouse effect is huge, but water vapor dominates. Now let's add clouds. Clouds reflect light away from Earth, they reflect heat down, they insulate, and they have their own internal radiative activity, not to mention electrical charges. I'm only showing nighttime data because that shows the greenhouse effect by itself. With clouds, there is more energy being re-radiated down to the surface. This is why cloudy nights are generally warmer than clear nights. The oceans generate our climate. These are nighttime figures for downwelling infrared radiation to the ocean surface. It depends on temperature, air pressure, and moisture, but CO2 likely contributes less than 20% to this. Remember that water vapor and CO2 cover the same wavelengths, so CO2 isn't really necessary when there's plenty of water. And since we know downwelling radiation can't penetrate the oceans, no amount of CO2 can heat the oceans, and I'm going to repeat that. No amount of CO2 can possibly heat the oceans because downwelling long-wave radiation doesn't have the energy to penetrate water. We've learned that CO2 plays a significant but minor role in the greenhouse effect. It can thermalize energy at the surface, absorb mechanical energy, and re-radiate it back down to the surface. And it dethermalizes a lot of the Earth's outgoing energy and sends that energy out to space. Now, I want to explain a key concept: saturation. This greenhouse gas molecule is carbon dioxide. Think of it like a little machine that runs forever. The molecule can do three things. 1, it can thermalize long-wave energy, absorbing long-wave photons and kicking nearby air molecules away at higher speed, heating them up. It can do this billions of times per second. 2, it can absorb a long-wave photon in the 14 to 16 micron band and emit another one in a random direction. If the random direction is down, it might go back toward the surface and start the process again. It does this on average about every 0.6 of a second, so less than once per second. 3, it can absorb an incoming air molecule's energy and transfer that energy out as a long-wave photon in a random direction. It also does this less than 1 per second, about 0.6 of a second. It does a lot of this at the top of the atmosphere where collisions are more rare. With these three functions, the CO2 molecule thermalizes billions of photons per second, sending energy into the air column from the surface, randomly re-radiates them on the way once in a while, and eventually takes that energy and sends it to space at the top. This is in the 14 to 16 micron band. Water vapor is even better at absorbing energy. It's a better emitter and dethermalizer, but there's less and less water vapor as you go up. Both CO2 and water vapor are so effective that the same amount of these molecules can feed more energy into the air column if more energy comes in from the sun. More CO2 won't help feed more energy into the system. As a thermalizer, water vapor is the same. In their capacity to thermalize energy, I would say that both CO2 and water vapor are unsaturated. They can thermalize far more energy than they are thermalizing now. This is a new term, so I want you to understand. I'm using it to describe the ability to absorb and thermalize energy, that is, to transfer energy mechanically to air molecules. Now I want to talk about the word saturated. You hear that CO2 is saturated in the 14 to 16 micron range, and some people say that's been debunked long ago. Here's what it really means. The right half of this diagram shows infrared radiation going to space and the various molecules that act as absorbers. The blue area shows where water vapor is effective. This corresponds to the yellow parts of the spectrum we saw earlier. Where the top of the area is flat, where it looks like a plateau, we say it is saturated. That means it easily absorbs all the long-wave photons in that range. More water vapor would not absorb more energy. It's saturated. Carbon dioxide absorbs mostly in a broad range from 12 to 18 microns, but you can see it looks like a bell shape. You see that flat top in the middle? That's where CO2 is saturated. That's the 14 to 16 micron band. In that range, CO2 can absorb any and all photons it encounters. On either side, we have the so-called wings, which is where more CO2 might be able to absorb a small amount more photons in these narrow wavelengths. But notice the right above that, water vapor overlaps the entire range, which means water molecules easily thermalize the same long-wave photons. Here's another way to see the same thing. This is a well-known graph by William Happer. It shows that CO2 is responsible for absorption near 700 wave numbers, which is 14 to 16 microns. The area above the curve represents absorption of photons. The squiggly gray line at the top shows the curve with no CO2. The magenta line below shows the absorption with 50 parts per million. See how much area is between the gray and magenta curves? That's how effective CO2 is as a greenhouse gas. But if we double CO2 to 100 parts per million, that's the green graph, which isn't much more absorption. Double again to get the light blue graph, and again there just isn't much more activity. You can see it's happening in the wings on the sides, like in the previous graph. Double again to today's 400 parts per million. It might be about 7% more than 50 parts per million, but this graph shows very diminishing returns. And if you double again to 800 parts per million, the red line, that'd be great for growing plants, and the difference in absorption from today would be very small. This is the saturation effect. The first 50 parts per million of CO2 is a very strong greenhouse gas. After that, there's hardly any greenhouse effect from more CO2. Since the Earth has always had at least 50 parts per million from the very beginning, there's no reason to think adding more CO2 will have any measurable effect on temperature. Because water vapor and CO2 are so good at absorbing photons, my concept of unsaturated corresponds exactly to this concept of saturated. Both water vapor and CO2 are saturated in their ability to absorb energy, and by the same token, they are unsaturated in their ability to thermalize that energy and turn it into heat. It is two sides of the same coin. It means that more CO2 can't and won't add any more heat to the atmosphere, and CO2 is very good at thermalizing all the photons in the 14 to 16 micron band. Now, if you look really hard, maybe there's a bit of room to thermalize a very small amount on the left wing, just above 13 microns, between 13 and 14 microns. But the effect of adding more CO2 in that one part of the spectrum is tiny. It's really splitting hairs. No atmospheric physicist disputes this concept of saturation. It's another nail in the coffin of the radiative model of understanding our climate.